Hello, this is Elliott Zaresky-Williams, CTO and co-founder of Neuralist, and today we're going to be talking about image classification with Neuralist, and this will be our third demo video. Okay, so what exactly is image classification? It's essentially you're trying to predict what group an image belongs to. For example, cats versus dogs. You show a network a picture of a cat or a dog, and it lets you tell you which one it is. So Neuralist lets you really rapidly prototype these simple convolutional neural networks, which are the specific model for image classification. For popular data sets like MNIST and CIFAR, but you also have it where you can train it on a custom data set. So whether you're new to machine learning and you kind of just want to play around with this without messing around with any code, you can try out MNIST and CIFAR. And then if you're a little more experienced or you want to use it in more practical applications, you can train it on custom data sets, and that's really a nice feature of Neuralist. So in this first part of the demo, we're going to train a CNN on the MNIST data set, and sort of talk about exactly how you get all the information you want after you train it. And then, so MNIST is a data set with 60,000 training samples of handwritten digits 0 through 9, and the testing size is 10,000 samples. And so for those of you who've never seen it before, the data set looks kind of like this. You have roughly equal distribution of all the digits, not exact, but close enough. And for those of you who've never seen a convolutional neural network before, essentially you have on the left your input image, and then what happens is the convolutional neural network learns to look at different regions of the image and then sort of shrinks the image slowly but surely, and then all the way to the very end, after you've extracted all the important information out of it, it learns to predict 0 through 9. And so that's essentially how this network works. And so the next part of this tutorial, we're gonna show exactly how to do this in Neuralist, with our GUI. Alright, see you guys in the next part. Okay, so let's actually get around to training our CNN on MNIST. So the way you run this file is the name of the file is run neuralistcnn.py. It's in your main directory like the other files in the demo videos were. And so in this case, your argument is going to be train path MNIST, and then you're going to put down one channel. So what exactly is the channel? So MNIST is a set of grayscale images, so it has essentially one channel. This will be fixed in the next update to where the code automatically detects the number of channels your data will have. But for now, just put one for that. And then we're going to do a batch size of 32. This is how many samples are fed into the network at once before you update it. Before you update the weights in the network. We're going to train it for 2 epochs, and we're going to do a learning rate of 2 times 10 to the minus 3. So let's just go ahead and hit enter and see exactly how this works. So you'll actually be able to make your own convolutional neural network right from the terminal very quickly. Okay, so let's enter in the channels for first layer. Let's just maybe put 8, and then maybe do 16, and then maybe 8 again, and then maybe conclude with 4. You don't want to make the network too large. And we'll do the kernel size. So the kernel size is really what square region of the image you're going to essentially slide over. So this is what these essentially are the groups of pixels the network looks at. And so it's typical for networks to use a kernel size of 3, so we're just going to use 3 for all 4 layers. Okay, and then we also have the hidden layer. So this is going to be the regular neural network that comes after the convolutional part. We're going to say 200 for those. And it uses 2 layers for this. Okay, now we're going to train it. And so you see here, we have you see the loss decreasing, and we're going to change up the print statements to look a little bit prettier in the next update. But essentially, this is we're going to let it train, and I'm just going to pause the video here because this will take a little while for it to actually finish training. So in the next part of the tutorial, we're going to see exactly how to look at the results and analyze how well the model did and so forth. Okay, now that we've trained our CNN, let's actually look at some results. But right before we get to that, let's actually just look at a couple lines above to see what's happening. So after the network finishes training, we're going to scroll all the way up to when that happens. It actually starts running through the test set. And the way that we have it set up right now in Neuralist is that it only runs through the test set after all the training epochs have finished, so only at the very, very end. We're going to have it in the next update where you can pick whether you want to run through the test set after every epoch or only at the end of training. But you see here, we train the network. It finishes, running through it all, and then what we'll do is it'll print out the predicted value for the test set for the batch size, which is the same as the training batch size, and then the ground truth. So what this really means is that the network predicts these numbers up here for the digits that it sees, and the ground truth are the actual digits. So we see that actually it's looking pretty good so far. But let's actually scroll down and see exactly how good we did on this data set. So we're going to scroll all the way down, and we're going to get down to our Python debugger. And so the way remember in the last few tutorials, the way we looked at our results, we just look at the model and we put in some predictions. But for the CNN, we actually store a lot of these results. So, and you access them by just typing in the variable results, and then if you put in keys, here's what you're going to get. You're going to essentially get a few directories. They're not really directories, but just, for people who are not as familiar with machine learning, we're going to ignore the fact that this is a dictionary for now. And then so we can go through train, test, and the model. So the model is where you save the parameters of it. So if you want to reuse the model for a later purpose, or train it again on another task, you have the option to just take the model after that if you're more familiar with how that works. Now let's actually just type that in right now. Actually, let's just do results. Let's take a look at the model we used. And you see here the parameters right here. The parameters are all here. That's essentially the model we had. Now, if you want to look at it in a not so numeric way, we're just going to type in model. So without using the directory. So here's the model we typed in the beginning. Remember, we had 8 channels. We had 8, 16, 32, and then 8. We did that in the first part of the tutorial. And you see here, we have the prelude activation, and we have just your basic 2-layer fully connected network at the end. So let's just, if we don't care so much about the model specifics, let's just kind of go back and look at what we did on the training data. So we do results.train. Let's take a look at all the information we get out of that. So for both training and test, we get to see the predicted values. So everything that ran through the model during the training phase and all the predictions are stored. Then we have the ground truth, which are all the actual labels the model saw. So all the handwritten digits, the correct ones, are stored here. Then we have the model loss. Then we have the precision score, the recall score, F1. Then we have the number of correct, the accuracy, then the confusion matrix. So in order to access them, we just do train results, bracket, in quotes, train, single quotes. We're gonna do some. Let's do correct. Let's see how many we got right. So we got 58,805 out of 60,000 right. That's pretty good. Now, if you want to do accuracy, let's scroll down a little bit so it's a little easier to see. 98% accurate on the training data set. That's looking pretty good. Now let's look at our F1 score. This is the last thing we'll take a look at before we move to the test set. So you see here we did pretty well across all the classes. So our training data is looking nice. Now let's see how we do on the test data. So we'll do test. Let's see correct. How many do we get right on the test data set? Not bad. 9,139 out of 10,000. So not that we necessarily need to do this, but let's look up the accuracy. 98.4. It rounds, of course. The accuracy does round. So we see we actually did slightly better on the test data set than we did the training data set. So this is actually a pretty strong performing model, which we always like. Now, let's take a look at a few of the predicted values. So we can do predicted. Let's do bracket. We'll do colon. Let's look at the first 10. So these are the first 10 that the network saw during the test phase. And let's see what the actual values were. So we do ground. And you see they all match. So it turns out that indeed, this model is looking pretty good. Now let's look at one more thing. Let's look at the confusion matrix. If I can type this out. There we go. So this is a confusion matrix. And remember, you want confusion matrix to ideally be just, you want it to be dominated along the diagonal. By dominated, I really just simply mean that you want very large numbers on the diagonal and very small numbers everywhere else. Ideally, you want 0 everywhere else. And this sort of tells you, exactly, what's the rows are going to be how many values are truly that class. So by that I mean like the rows are going to be the true ones, the correct ones, and correct 2s, 3s, and so on. Then the columns will be the predicted ones, and there's basically how often it's predicted is going to be, it's at a specific row and column entry. I won't get into the details of that for this tutorial, but you can always look up confusion matrix, if you are curious about more how it works. But anyway, so that is really how the CNNs work. And in terms of technical points to note, is that the networks we use are regular convolutional with 2 fully connected layers at the end, and you specify how many nodes you want. And then if we exit out of this, I just kind of go back to our original script. So here we have, we have our learning rate set to e to the minus 3, but we can add parameters like, weight decay, we can change the number of layers and, and so on. So feel free to look at the documentation so you can see exactly how many different arguments you can play around with, but it's very versatile in what you can do with it. So this concludes the tutorial part on MNIST. Now we're going to talk about how to do this for custom data sets, which is where the really exciting parts come into play. Okay, so before we get into actually how to train in a custom data set, we should first understand exactly how Neuralist expects us to have our data loaded. So we're going to go to Notebook Demo, and we see here that we have this. So this is our main directory, and under the main directory for our data set, we want to have 2 folders for train and validation. You can do train, test, but val's a good name. So because Neuralist is going to expect a subfolder for train, a subfolder for validation, and then if you go under each of these folders, you'll see that there are 4 different subfolders that contain the images we want. Like if we go to ants, we have ants. If we go to bees, we have bees, and we're essentially going to be classifying, making a CNN that can classify this data set. Now, of course, it's not going to be highly performed because the data set's very small, but it sort of just gives an idea of how exactly the user can train their own data set. And this is sort of just more for demo purposes. And so, in validation, it'll be the same thing. We should see that a main folder that contains training and validation, and in that main folder there are these 2 subfolders, train and validation, train and val if you want. And then in each of these folders there should be subfolders for the number of classes. So we have 4 classes: ants, bees, butterflies, and moths, and each of these should have PNGs or JPEGs. So that's the format that it expects us to have our data into. So if you follow that format, as long as you have JPEGs and PNGs, you could classify anything you want to for these images, as long as you label it correctly. So that's just really all there is to that's really how simple it is to train on your own data set. Okay, so you see here, we go back to, our Python file, run neuralist cnn.py. We have our train path, which is like I was saying, we go to, the image data sets, notebook demo, and we have our train folder and our validation folder. And then we're going to do a learning rate of 5 times 10 to the minus 4, and then I'll do 20 epochs and a batch size of 6. And this data set's very small, so it's going to kind of blow through it very quickly. If we look at the data set, there are really not that many samples, and it shouldn't perform that well on this data set. We'll just see how it goes. Let's say maybe 100 for this. So you see now it's training. It's going through all the epochs. And then one thing to expect is that I think that if you're training networks on your own custom data set, it's good to have maybe a couple hundred at least of each sample. We do plan on actually adding in few shot learning, where essentially you're able to train networks on a smaller number of samples than we typically use. So that right now in the Neuralist beta, we only have traditional CNN training, which is using cross entropy loss for large data sets. So it's almost done training. Okay, and so it ran through the test set. So you see it did not do so well on the test set, but we're going to see exactly how poorly it did. So again, we go to results. And of course, results, has the same information as before. It's a little small this time because there are fewer samples. So, we have keys, same as before, like we did with MNIST. Then we're going to do, let's see, results. Let's look at the test data set. So, okay, actually for the, well, let me just make it a little easier to see, because all information, of course, is here. We only want to look at one at a time because it makes our life a lot easier. So let's just look at predicted. Okay, so it looks like in our test data set, which is sort of small, we only predicted the first class, but indexed by 0, because the indexing starts at 0. So that means we only predicted ants. Now, let's look at the actual test data. So you see here there was a mix. So it turns out there were only 1, 2, 3, 4 ants in that test data set. So we can see that it missed most of these. And this is not too uncommon when data set is small. The neural network only just learns to predict one class, and it doesn't really learn how to distinguish between that and other classes. But that's okay. The point is that we're able to take a data set as simply as I just simply as I explained in the last section, and with the folder structure, and just simply train the network that quickly. And of course, with a large enough data set, this should perform very, very well, just like we saw for MNIST. And of course, if you wanted to combine data sets together, all you really need to do is just really drag and drop into your folder and into the appropriate folders, and then you're really good to go. The sky's the limit with what you can do with this with a large enough data set. So I hope you guys enjoyed this introduction to image classification, and we'll see you guys in the next tutorial. Thanks for watching.